Okay. So yes, let's hear it for the K-State Wildcats.
Woo!
Yay.
Purple tie.
Okay. All right. So let's chit chat about the lab now that you know how the big picture was. So on this quiz on Friday, first off, you need to know 6 of the strong acids in the formulas. Okay. It's going to be the same situation. I'm going to give you blank lines. Here's the force. Write out the formula. Write out the names. And again, you can get most of them just from the list of halogens. Okay, there's a big chunk of them right there. Okay, so now that you all are done with the lab, let's kind of paint the big picture. So the first thing that you did was that you found the molarity of the sodium hydroxide. And basically took KHP, that reacted with the sodium hydroxide, and out of that, basically the KHP neutralized the sodium hydroxide. So what you did is that you started with a certain number of grams of KHP, and you said, okay, molar mass of KHP is 204.2 grams per 1 mole of KHP. KHP reacts with sodium hydroxide in a 1-to-1 ratio, okay, because it's just basically transposing the sodium and a hydrogen. And then you divided that by the volume of however much it took for that solution to turn pink. Out of that, you calculated the molarity of your KHP, of your sodium hydroxide, which hopefully is something around 0.1, because that's what I shot for when I mixed up the lab. Okay, I think that's about what everybody got. So you should have 3 trials. I should be able to see your average. I want to see one complete calculation like this. Okay, and I promise you, at some point on an assessment near you, you're going to have to be able to do this calculation. So understand what values that you really need to have in the calculation. Did you need the fact that you added about 100 milliliters of water? Or did you know that you needed that exact amount of volume of your sodium hydroxide? So when you go back and you're looking at this calculation on this lab, make sure that you understand what values did I need to know exactly in terms of volume, and which volumes were, they're there, but I didn't need that in terms of the calculation, okay? So make sure that you got that. So then after you got that part done, then you took a beaker, you added exactly 25 milliliters of acetic acid, okay? And then you titrated that with your sodium hydroxide, and at this point, you kept track of the pH. So you generated a curve of pH versus volume, probably looks something like this, okay? And out of this, you're going to find 2 important things. You're going to find the midpoint of this graph, and that's going to be your equivalence point, okay? So here's what you have to understand at that equivalence point. This reaction, and I'm going to write this as the molecular form of the acid because it's acetic acid, because it's a weak acid. So I'm going to write this as HA. I'm not going to write it as H+. I would write it as H+, like if we were titrating like hydrochloric acid or nitric acid. If we were titrating this as a strong acid, my equation, I would just put H+, because it's only the hydronium ions that I'm going to worry about. But because of the fact that this is a weak acid, I have to worry about the fact that, number one, this is existing as the molecular form of the acid. That's going to react with hydroxides. I'm not going to put the sodium because I could care less about the sodium because it's just a spectator ion. And out of this, I'm going to get water and anions. Now, here's what's important. This is what I showed you all yesterday. If we had titrated hydrochloric acid, I wouldn't worry about the concentration of my chloride ions, because the chloride ions don't react back with the water to reform hydrochloric acid. But what you'll see out of today is that the right side of this equation, where you have that anion with the water, that's just as important, if not more important, than what's happening on the left side. So there's two huge differences that you have to keep track of. What's happening if you titrate a strong acid, strong base, versus what happens if you titrate a weak acid with a weak base. Starts off, first off, in the difference in how you write your net ionic equation. So on your reaction, if this situation, because it's a weak acid, I'm going to write it as the molecular form, because that's how it's existing. So basically, what's happening is this. On a rice chart, you're saying, okay, I'm going to have a certain number of moles of your acid. And you can find that by taking the molarity times the volume. Okay, that's the idea. So I'm just going to make up a number, and let's say that's 0.2 moles, because when I take my molarity, which is moles per liter, and I multiply that by my volume in liters, I get moles. So when you're titrating, listen to me very, very carefully. When you are titrating, this is all about moles, or a new concept we'll talk about today called millimoles. It's the same idea. When you are titrating and when a reaction is taking place, you do not work off of molarity. You have to work off moles. You have to work off of millimoles. You cannot work off of molarity. So here's the basic idea, is that as you add more and more hydroxide, the number of moles of acid in that beaker is decreasing, because that hydroxide is reacting with the acid. And the hydroxide comes up to the acid and says, give me your protons. You missed it. Give me your protons. And the acid goes, hey, even though I'm a weak acid, I'm attracted to this, go ahead and take it. So the hydroxide basically takes the hydrogen from this, and it makes water. And you have an anion that's left over, okay? So after the robbery, you form water in the anion, okay? But the anion will get its vengeance later on. So what's going to happen is that over a period of time, the concentration of my acid is going to drop, and the concentration of my anion is going to increase, okay? So if you were to draw a graph of versus time, so this would be the concentration of your Ha, this is the concentration of your anion, this is going to go up, this is going to go down. At some point, you won't have any anion left, or you won't have any of the molecular form of the acid left. When that happens, when you don't have any Ha left, all your Ha is gone, okay, you're O for Ha. At the equilibrium point, your Ha is gone, okay, you're Ha-less, okay, you got no Ha. And all the hydroxide is used up too, because you took all the hydroxide and you used that. So if you start with like 0.2 moles of Ha, to react with that, that's going to take 0.2 moles of O, okay? And those become zero. But what's going to happen is that if you start with 0.2 moles of Ha, that means you're going to generate 0.2 moles of your anion, because it's a 1-to-1 ratio. So over a period of time, the concentration of your acid is going to drop. The concentration of your anion is going to go up. So at that point, at that equivalence point, the moles of acid equals the moles of your base. So that's what allows you to use MAVA equals MVVB. This is a cute little equation. But understand where it comes from. This isn't just, oh, we'll just randomly make up MAVA equals MVVB, okay? No, okay? It isn't just random thing. This works because the moles of acid is going to equal the moles of base. And this doesn't matter whether it's a strong acid or a weak acid. It's the same idea. Okay, it's the exact same idea. Moles have to equal the moles. So, here's the story. You know the volume of the acid that you added. You know that was 25 milliliters. You're going to go to your graph and you're gonna find the volume of the base at the equivalence point. Probably around 27, 28 milliliters, okay? Just guess, okay? You're gonna know the molarity of the base because that's what you found first. So the only thing you don't know is the molarity of the acid. So what did somebody get for the molarity of their acid, of that acetic acid? Hopefully it's somewhere around 0.1.
0.12.
Okay, cool. That's kind of what I was shooting for. So you're going to do this 3 times. You're going to have 3 different graphs. And here's what there are 3 lines I want to see on every graph. Count them, 3 lines. I want to see the line coming down at the equivalence point. That's line number 1. So there's your equivalent point line. Then I want to see a line at half the equivalence point. Okay, that's the second line. And then from here, I want to see a line coming over here that indicates that pH at half the equivalence point. So I'm going to look at every graph, and I want to see 3 lines. 1, 2, 3. Okay, 3 lines, every graph. Got it. Okay. Now, let's talk about some of the questions. So, the first one, write the neutralization reaction between sodium hydroxide and hydrochloric acid. Okay? If you want to do like the Chem Jan version of this, you can just put NaOH plus HCl yielding water plus sodium chloride. Okay? Anytime you neutralize an acid with a sodium hydroxide, basically you get water and a salt. Okay? So, on number 2, you're going to figure out, hey, what volume of 0.125 molar sodium hydroxide would be required to neutralize 60 milliliters of 0.25 molar hydrochloric acid? Don't get wrapped up in, oh, I'm going to randomly chuck numbers down. Understand, when this thing is neutralized, that the moles of acid is going to equal the moles of the base. Okay, that's the basic idea. So you can do this as a pure stoichiometry thing. You can start off with 0.060 liters of HCl, and then you can go, oh, I know the molarity of my HCl, so 1 liter of HCl contains 0.25 moles of HCl, and then you can do the stoic and go moles of HCl into moles of sodium hydroxide, and then your last step is that you know the molarity of your sodium hydroxide. So that's an option if you want to do pure stoic. Okay, if you want to use MAVA equals MVVB, that's cool too. Okay, but that answer on number 2 in milliliters should be between 100 and 150. Okay. Now, here's what you want to look at with this when you get to number 3. Okay, and let me show you the 2 different ways you can work number 3. So, again, I cannot emphasize this enough. You have to know what's happening in the reaction. So I'm just going to write the net ionic for this because it's going to save us some time. Because it's a strong acid, the nuts and bolts of this is that I'm just going to worry about this. I'm not going to worry about the anion concentration. I don't worry about the anion concentration. You okay, John? Yeah. Okay. I'm not going to worry about the anion concentration because the anion does not react with the water. If it had been a weak acid, which we'll see later on, I would worry about that. But I'm not. This is just a strong acid, strong base. The only thing I'm worried about is the hydronium and the hydroxide. So up to this point, if you were to find moles, you would take the volume in liters and you would multiply that by the molarity, which is moles per 1 liter. The liters would cancel out, you would get moles. That's what you all have done. That's what you've done up to this point. Now, there's a new idea that you can use. This is a personal preference thing. you can use what's called millimoles, okay, which sounds like something out of Disney. Hi, I'm Mickey. Let's talk about millimoles. Okay? Not really. But here's the story. So what this does is that it saves you the hassle of converting liters into, converting milliliters into liters. So what you can do, and this is a personal preference, I like this because I hate dividing by thousands. So if you look on number 3, you have 60 milliliters of a 0.25 molar solution of hydrochloric acid. So to get millimoles, you take your volume and you just leave it in milliliters. Okay, that's where the millimoles comes from. And then you just multiply that by the molarity. Okay, it saves you going through and dividing by 1,000. So, like on this one, if you take that 60 milliliters times 0.25 on your net ionic equation, so here's your rice chart. I'm going to start, if I take that 60 times the 0.25, I would have 15 millimoles of my hydronium ions, okay? That's what I have to work with. Now, then I'm going to mix that with 60 milliliters of 0.125 molar solution of sodium hydroxide. Again, if you take 60 times 0.125, you get 7.5 millimoles. Okay? And it's milliliters with a capital M on the end of it. So at this point, here's what I want you to see. Is that I have 7.5 millimoles of base and 15 millimoles of my acid. So at this point, all of that hydroxide is going to get used up. So that's just going to go to 0. I've added it, it's going to get used up because it's going to react with the acid. And that's the same amount that I'm going to subtract from my hydronium ion concentration. So, that becomes 7.5. So what that tells me is that I have 7.5 millimoles of acid that is still remaining in that beaker. Okay? Now, if this had been a weak acid, at this point I'd go, it's half neutralized. My pH would equal my pKa. If this had been a weak acid. It's a strong acid. I can't do that because I don't know what my pKa is because it's a strong acid and strong acids don't have Ka values. So if it had been a weak acid, I'm done. pH equals pKa. There you go. I take the negative log of my Ka value. If that's what I've got, boom, I'm done. Okay? Can't do that. But here's the bigger idea, is that I have 7.5 millimoles of this acid that is left over. So what I need to find is the pH. So to find the pH, I need to take the negative log of my hydronium ion concentration. This is not my concentration. That just tells me how many millimoles I have. Yes?
How come on this one you don't make it because doesn't it take 2 hydrogen? Or no, it's OH. Okay, never mind. Yes.
Good?
Yeah, I was so confused. I was like, wait, that doesn't make sense. But now
We are
I get
recording this, aren't we?
Huh?
We are recording this, aren't we?
Yes.
Okay. I thought about that. Okay. So that's why it's a 1-to-1 ratio.
Yes, I was thinking that there wasn't an H on the OH for some reason. So I was like, what?
Yeah, there is.
Yeah, I know there is.
Yeah.
I got that now.
Okay. Now, listen to me. When you see square brackets, that's molarity. It has to be molarity, not millimoles. It has to be molarity. So to get to this value, I have 7.5 millimoles of my acid. I have to divide it by the total volume that's in that solution. So I have 7.5 millimoles. I've added 60 milliliters of acid, 60 milliliters of my base. So my total volume is 120 milliliters. So to get this concentration, I'm going to take those 7.5 millimoles and divide that by that total volume of 120 milliliters. My milliliters cancel out. I have molarity, that's what I'm after, that's what I can put in here, okay? Now, if you're old school, you go, Burkamp, had a bad experience at Disney World, man, can't do with the millimole thing, right? Bad experience on some of the rides there, sorry, okay? So if you want to work in moles, that's cool. If you want to take that 60 milliliters, divide that by 1,000, get 0.06, multiply that by that molarity, you can do that. You're just going to get really small numbers and you're going to be dealing with a lot of decimals. Okay, but you're going to get the exact same answer. But again, the whole idea is that you have to figure out what's in excess. Do you have excess hydronium ions? Do you have excess hydroxide ions? And because this is only half neutralized, that means I still have some acid that's in that solution. Okay? So at some point, you either divide by the total volume. If you've worked in moles, which is cool, then you have to divide by the total volume in liters. If you don't like that, and you like this idea of millimoles, like, Burkamp, I hate decimals. Okay? I was the president of the whole number club. Happy for you. Okay? Then leave it in millimoles, and divide by the total volume in milliliters. But your pH of number 3 would make a horrible, horrible, horrible GPA. Zach just is blue. Okay. Your answers to 4 and 6 should be the same answer, and both of those should be less than 1. I have no idea. Now, when you get, let's talk about what I want you to see on number 8, and this is what I showed you all yesterday, okay? So this is the stick-up situation. So you have sodium acetate, NaC2H3O2. Sodium acetate, it's white powder. Soluble in water because it's a group 1. This dissolves, and along comes a water molecule. Okay? So first off, it's going to be attracted to the hydrogen into the water molecule because the hydrogen into the water molecule is positively charged. So not only is it attracted to it, it comes up to it and says, this is a stick-up, give me one of your protons. The water molecule says, hey, I don't want any problem, man. Chill out. I don't want any problem. Take a proton, but we didn't like him anyway. Dweeb. So it's always positive bastard. Hi, I'm positive. Get away. So what's going to happen is that you're going to reform the acid, and you're going to get some hydroxide ions. So this is what you have to begin to understand, is that you dump sodium acetate in water, you start a secondary reaction that reforms the acid, and you kick out hydroxide ions, which makes the pH go up because you're generating hydroxide ions. Now, this only happens, listen to me, this only happens if the conjugate, if the anion is the conjugate base off of a weak acid. If the conjugate base is off of a strong acid, this doesn't happen because you're not going to reform the acid anyway because it's a strong acid and you care less about reforming and making the acid itself. So this is how you can tell that the conjugate base off of a salt is off of a weak acid. Dump it in water. If you see the pH go up, that means that you have started a secondary reaction and you're generating hydroxide ions. You dump it in water, there's no change in pH, that tells you that your anion is the conjugate base off of a weak acid because it doesn't reform that, okay? Or off of a strong acid, excuse me. So that's the basic idea of 7 and 8 when you go to answer those, okay? On that first page. Now, what I want you to see on number 7 is, as screwed up as it is, you're basically taking your acetate ion, you're reacting with water, and you're going to reform sodium acetate and hydroxides. This is what I want for number 9. This is the shortcut version of it, okay? You need to do like the full-blown thing. The anion plus the water reforms the acid and the hydroxides. Now, when you get to number 13, and it said, write the dissociation equation for acetic acid. All I want on number 13 is that you're going to just go, hey, HC2H3O2 turns into hydroniums plus C2H3O2 minus. That's all I want from number 13. Do not make number 13 difficult. Evan.
So, going back to like number 8, I get that, and I guess it's kind of all these questions. I get that it breaks apart and it reforms the acetic acid and the OH. And I get that the OH would raise the pH.
Yes.
But then, what's the acid doing? Because wouldn't the acid then work to lower the pH?
No, because remember, fundamentally how you measure pH is the availability of free hydronium ions. Those hydronium ions aren't floating around, they're bound up with that anion.
Okay.
Okay? They're there, but they're not free to measure, they're not free to move
So
around.
then how would that affect like the defining of conjugate base and conjugate acid?
What do you mean?
Well, like how would you know which one is which?
Well, because with this one, if you look at this, okay, the acetate is acting as the base, the water is acting as the acid. So the water, the sodium acetate would be the conjugate acid, the hydroxide would be the conjugate base.
Okay.
Okay?
Yeah.
Now, when you get to number 18, okay, I given you the Ka value. Remember that your Ka times your Kb equals that autoionization constant of water, which is 1.0 times 10 to the negative 14th. So your answer to number 18 should be something times 10 to the negative 10th. Okay? Now, when you get to number 19, what is the concentration of hydronium ions in the pH of a 0.5 molar solution of acetic acid? Okay? So, on number 19, you're going to go old school. You're going to go, here's my acetic acid. It's going to ionize into hydronium ions and anions. You have the 0.5 molar solution of this. This is 0, 0, minus x, plus x, plus x. This becomes 0.5, this becomes x, this becomes x. Old school, okay? Now, here's what I want you to see is the difference. On number 19, there's no hydroxides involved. On number 19, we are not neutralizing this acid. Okay, we're not, there's no reaction. The only thing you have is acetic acid. There's no hydroxides here. All that's happening is this stuff is ionizing. And here's the bigger picture. And this is going to be important when you get to number 21. Mother Nature likes equilibrium. Okay, Mother Nature is all about equilibrium. So that's your Ka times your hydronium times your anion divided by HA. Now in this situation, both of these are X's, okay? Because there was no anion to start with. Both of these are X's. So Mother Nature goes, hey, I want that Ka value to be 1.85 times 10 to the negative fifth. So she's going to figure out what values of that hydronium and that anion together produce that Ka value, because that's when Mother Nature is at equilibrium. Okay? So if all goes well, your pH on number 19 is going to be somewhere between 2 and 3. Okay? 2 and 3. Now, here's what's happening on 20. Here's the difference on number 20. It's still the same initial reaction, hydroniums plus anions. Okay? And here's the bigger idea. Mother Nature still wants that same Ka value of your hydronium ion times your anion divided by the concentration of your acid. Okay? Mother Nature still wants that to happen because Mother Nature is the lazy prima donna. Okay? Now here's the difference. What's happening on 20 is that this is what we're going to call a buffered solution. So instead of that anion concentration starting at 0, what we've done is we've overloaded it. We've already put a high concentration of anions in the solution because we put sodium acetate in them. So what's going to happen here is instead of that anion starting at 0, like you're used to, it's a little bit of a curveball. Now, that's going to start at 0.75, okay? The hydrogen acid, the acid itself, is going to start at 0.50. Hydroniums are still going to start at 0, okay? So here's what's different from every other problem that you have done. Every other time, the anion starts at 0. This one, it doesn't. It starts at 0.75. But here's what's still true. You're still going to go minus X, plus X, plus X. That's still going to be 0.50. This is going to become X. That's going to be 0.75. Now, here's what's different. At this point, you know what the anion concentration is. Your anion concentration isn't X. Your anion concentration is 0.75. Your Ka is still your Ka, and your Ha is still 0.50. So in this situation, you're just solving for X. You're not solving for X squared. You're solving for X. So mathematically, you need to multiply by Ha and then divide by that anion. Okay? You're not going to take the square root of it like you're used to. Okay? You've got to think through this. It's like, Mr. Workamp, tricky you are. So you need to solve for X, which you did before, but before it's just been X times X. This time X is by itself because you know that's going to be 0.75. Now, here's the kicker. Okay? Here's the kicker. Mother Nature still wants the same Ka value because Mother Nature's the lazy prima donna. So Mother Nature mathematically is going to make that hydronium times that anion concentration divided by the concentration of that acid still equal 1.85 times 10 to the negative fifth because Mother Nature likes equilibrium. She wants to chill out with gray hair, Birkenstocks, tie-dye, and smoke on that hookah pipe. And she only does that when she's in equilibrium. So what you're going to see is that this X here is much smaller than the previous answer because of the fact that it doesn't take very many hydronium ions here to get that same Ka value. So what you should see is that your pH on number 20, this is an ish, should be around 5. Okay? So your pH on 19 and the concentration of your hydronium ions is like 10 to the negative third. On 20, the concentration of your hydronium ions is 10 to the negative fifth. So here's what's common. Mother Nature still wants the same Ka value. But when you already start with a bunch of anions, it doesn't take as many hydronium ions to get to that same Ka value. So when you answer 21, I say explain the differences and similarities in your answers and calculations to number 19 and 20. Okay? You want to say, here's the similarities, here's the differences. Here's the most important similarity that you have to understand. Mother Nature wants to be in equilibrium, and mathematically, Mother Nature wants that same Ka value. That's the most common similarity. What's different is that mathematically, what happens to that hydronium and anion concentration to get to that same Ka value. Okay? That's how you want to approach that one. Okay? Anybody have any questions other than that on the lab? Ema?
I'm good.
Okay. All right. Now, for those of you that are new to my teaching style, and this has become a new phenomenon probably the last 3 or 4 years, when you answer the question, don't restate it. Okay, I know what the question is. I wrote the questions. Okay, don't restate the question. It's annoying because then I have to spend a lot of time reading the words that I wrote, okay? I know what the questions are. Also, there's two words I hate when you answer questions. What are the two words that I hate?
Different.
Different and
Change.
way too nebulous. It's different. Oh, it changes. Okay? No. State it increases, it decreases. Why does it increase or decrease? Just don't go, it's different. No. Way too nebulous. Okay? All right. Anything else going on? Let's go try solar. So here's what I want. Okay? Here's the sequence of things that I want. So, basically, let's see this stuff. So I want sheet, yellow sheet on top. Okay? Then blue sheet. Okay? And start when have that where it starts with the concentration of the unknown acid. So yellow sheet like this, blue sheet like this, and then the three graphs like that, stapled together. That's what I need. Okay.
What do you want us to do if we have an extra sheet?
Just okay. So, in all my classes, this is the only time this is ever going to happen. We're actually going to kind of work through the same process 2 days in a row about how you do the neutralization of strong acids, weak acids in different situations. Okay? It's one of those important skills that you have to get, and because it ties in so many different things. So, today we're going to work through this. I'm going to show you how the different processes work. So the first thing you're going to have is that I'm just going to give you 50 milliliters of benzoic acid, has a Ka value 6.3 times 10 to the negative fifth. And the first thing, all I want you to do is calculate the initial pH. Okay? We have not titrated this thing. We have not added any hydroxide ions to it. Nothing. Okay? The only thing that exists in that beaker is benzoic acid. That's it. Okay? Now, and I cannot emphasize this enough, you have to understand what's happening in the reaction. Set up these rice charts. So you go, okay, all right, I can play this game, Burkamp. Okay? Now, if you really want to write out the big formula for benzoic acid, you can. Just use Ha. That just makes it simpler. So basically, Ha is going to turn into hydronium ions and anions. Technically, there's water there. If you're hardcore, it's like, Burkamp, I really like writing water molecules. I was president of the water club. Fine. Okay, you can put in water and you can make that H3O plus if you really want to. Whatever works. Now, here's the deal. This is a 0.2 molar solution. Okay? So, if you're just dealing with just the acid without any hydroxides, you can work in molarity. Okay? There's no need to work in millimoles because it's not going to do you any good anyway, because all that's going to happen is that you just work in molarity. This is old school, just like you've done before. So you're just going to go, okay, 0.200, I've not added any anions to it. It's just old school. Minus X plus X plus X. That's 0.2 XX. Ka equals X squared over Ha. And to save us some time, if you do this, you get a pH of 2.45. Okay? So if you take Ha times Ka, the square root of that, take the negative log of that, you get a pH of 2.45. Okay, so that's my theoretical initial pH, 2.45. Okay? Old school. Everybody should be able to look at that and go, Burkamp, we got you. Okay? Now, what we're going to begin to do now is we're going to begin to add base to it. So, I'm going to start with that 50 milliliters of 0.2 molar benzoic acid. Okay? Now, the first thing I'm going to do is that I'm going to add 15 milliliters of a 0.2 molar solution of sodium hydroxide. Okay, so imagine this. I've got 50 milliliters of a 0.2 molar solution of your acid. It's sitting there in the beaker. you're going to crank open the valve, and you're going to add 15 milliliters of sodium hydroxide to this, okay? What I want to know is what's going to be my pH at this point. Now, clearly, what should my pH be relative to 2.45, above or below?
Above.
Above, okay? So, now, here's going to be the difference. When you set up that rice chart, here's what's going to change. First off, I'm going to write that as the molecular form of the acid. And it's existing as the molecular form of the acid because it's a weak acid. If it had been a strong acid, I could just put hydronium ions because it's a strong acid. Well, it's a weak acid, which means it's going to exist as the molecular form. I'm going to add some hydroxides to it. I'm going to get some water. And I'm going to get some anions. Okay? Now, if this was a strong acid, like hydrochloric acid, I wouldn't worry about the anion concentration because the anion isn't going to react back with the water. But because that conjugate base wants to reform that acid, I have to take that into account. Now, I'm going to work in millimoles, okay? Because it's going to save me some hassle dividing by 1,000. I'm going to get some nice numbers to work out. So if you do the math, you have, if you take 50 times 0.2, so if I take 50 times 0.2, I get 10 millimoles of my acid. If I take 15 times 0.2, I get 3 millimoles of my base, and my anion concentration is going to start off at 0. Okay? Now, all of my base is going to get used up. Okay? So this is going to go to 0. This is going to become 7 millimoles. I'm going to, because that's a 1-to-1 ratio, which means that I'm going to make 3 millimoles of my anions. Okay? Now, at this point, I'm going to show you 2 ways that you can work this problem. This is a personal preference thing. Okay? One is more pure mathematical and more technically correct. The other one's more of a shortcut mathematically. Okay? So we're going to go through the big process first, because this is the bigger idea. Mother Nature wants that Ka value to exist, which is going to be that hydronium ion times the anion concentration divided by Ha. Okay? Now, at this point, I have the capacity to know what the concentration of my acid is. I can take 7 millimoles and divide that by the total volume and get the concentration of my acid. Okay? So, what I would do, okay, you could take the 7 millimoles, because that's the remainder of my acid, and divide that by the total volume in this case, which would be 65 milliliters. Now, I'm just going to park that there. Okay? I'm just going to park it there. Now, the concentration of my anions is going to be 3 millimoles divided by the concentration of 65, or the total volume is 65 milliliters. And I know what my Ka value is. Now, because I'm dividing by the same total volume of 65 milliliters, in effect, what's going to happen? It's going to cancel out. Okay? So, technically, you need to take the millimoles and you divide it by the total volume. But it's going to work out to be the same ratio anyway. So I can just leave this as 3 millimoles and 7 millimoles. Technically, it's molarity, but what's a common denominator between friends? Okay? We'll just keep it on the down low. Now, what you don't know is your hydronium ion concentration. So I can take my Ka times 7 millimoles, divide that by 3 millimoles, and understand what you are finding. You are finding your hydronium ion concentration at that point. Okay? You're going to get this number. Then to get the pH, you're going to take the negative log of what you get out of that calculation. Okay? Pure chemistry-wise, this is the best method. Oh, I'm solving for my hydroniums. I know what my Ka value is. I want Mother Nature to be in equilibrium. It's all good, okay? Quite a bit of algebra. You have to get your hydronium ion concentration by itself, and then you have to take the negative log of that. If you're hardcore, go Berkamp. You chemistry were tight, pure chemist, pure mathematics. Go with that. Works. It's cool. Here's the more, I'll call it efficient method, okay? And this is this Henderson-Hasselbeck equation, which says pH equals pKa plus the log of your anion concentration divided by the concentration of your acid. Now, we need this number. Somebody take the negative log of the Ka of acetic acid. Somebody take the negative log of 6.3 times 10 to the negative fifth.
4.201.
What'd you get?
4.201.
So call it 4.20. Okay? Because I just went 2 decimal places to the right. So here's the beauty of this method. That pKa is never going to change. Okay? It is never going to change. Once you do that calculation, you never have to do it again. It's done. 4.20. This is like the root of the tree, and everything is going to branch off from this. 4.20. Boom. Here we go. Now, plus the log. Now, we're going to do a little bit of venture into a little bit of mathematical analysis. Now, technically, these are brackets. Technically, I need a concentration in molarity. But here's where the magic happens. That's 3 millimoles divided by the total volume, 65 milliliters. That's 7 millimoles divided by the total volume is 65 milliliters. Again, what's going to happen to the 65 milliliters? It cancels out. So basically, you can take the ratio, you can take the log of 3 divided by 7. Now, before you do that, step away from the calculator, step away from the calculator. You're taking the log of a value less than 1. That's 3 divided by 7. When you take the log of a value less than 1, is that a positive or negative value? Negative. So this is going to become a negative value. So my pH has to be less than 4.2. Now, here's the advantage of this. This generates the pH straight up. You don't have to find the hydronium ion concentration by itself and then take the negative log of that. This is just straight up, boom, here you go, plug and chug, that's it. So if you do this right, you should get 3.83 as your pH. Now, this should make sense. Your initial pH when it was just the benzoic acid was 2.54. We've added some base to it. pH has gone up, okay? Because what's happening, and again, on a molecular level, you have to understand what's happening. As this reaction is taking place, there are 2 things that are changing. The concentration of my Ha is going down. The concentration of my Ah is going up. Okay? So I'm generating anions. I'm decreasing the concentration of my acids. We're not half neutralized at this point. Okay? We're still on the left side of that neutralization curve. Okay? We're not half neutralized. Now, next step. I'm going to start over with that 50 milliliters of 0.2 molar solution of benzoic acid. Okay? But now I'm going to add 25 milliliters of a 0.2 molar solution of sodium hydroxide. Okay? Rice chart. It's nice, it's rice. HA, my hydroxides, going to yield el agua and my anions. Now, I'm still going to start off with my 10 millimoles of my acid. Okay? You take 50 times 0.2, you're going to get your 10. If I take 25 times 0.2, I get 5 millimoles of my hydroxide. That's going to start off at 0. It's like we're starting over from scratch again. Okay? Don't let the previous reaction take place. It's like you're starting over from scratch. Evan,
And we don't care about the sodium, right?
sodium's a spectator ion. Sodium is not part of this story.
Okay.
It's there, not part of the story.
It's just there to.
It's like a freshman out in the hallway. They're there, not part of the
The
story.
NaOH completely dissociates.
Yes, because sodium is group 1, which means it's completely soluble. Okay?
All right.
Now, at this point, hopefully some of you go, oh, I see what's going to happen here. 5. How much of that acid have we neutralized?
That's good.
Half of it. When you half neutralize it, and it's a weak acid, what does your pH equal? Oh, your pKa. Oh, this is cool. It's kind of punchy. Okay. Now, if you don't believe me, go pH equals my pKa, which we have already found to be 4.20.
4.20. Sorry, 4.20.
Now, my anion concentration is going to be 5 millimoles divided by the total volume. That's going to be 5 millimoles divided by the total volume. You're taking the log of 1 is
0.
goes away, pH equals to pKa. Okay? Don't have to do the math. Now listen to me very carefully. That only works. Listen to me very carefully. You can only do that when it is exactly half neutralized. Okay? Now, to save some time. Now we're going to add 45 milliliters of 0.2 molar solution of sodium hydroxide. Okay? So it's the same reaction. So we've got 10 millimoles of my acid. If you do this math, we're going to have 9 millimoles of my base, and that's going to be 0, minus 9, plus 9, I get 9, I get 0, I get 1. Okay? So the beauty of this Henderson-Hasselbeck is once you kind of lay out the matrix, then they all kind of work the same way. So now, I'm going to have the pH of 4.20 plus the log of my anion concentration of 9 divided by 1. Now, here's what I want you to look at. Now I'm going to take the log of 9. I'm going to take the log of a value bigger than 1. So is this term over here a positive or negative value? Positive. So my pH is going to be above my pKa. Because now I'm going to have a lot more anions than I am going to have as the molecular form of the acid. So if you do this math, you get 5.15. Oh, that's kind of cool, right? pH has gone up. So we went from 2.54, we went to 4.2, and now we're all the way up to 5.15. We're not neutralized. Close. Now, here is the most complicated step. Okay, and you have to work like 3 different steps on this next problem. So, pay attention to here. So, at this point, I'm going to add 50 milliliters of my 0.2 molar benzoic acid, and I'm going to add 50 milliliters of 0.2 molar sodium hydroxide. Okay? So, Ha plus O yields Pula, if you speak Setswana, and an anion. Now, here's where the magic happens. This is 10 millimoles, this is 10 millimoles, this is 0. So what's going to happen now? I have 10 millimoles of acid, I have 10 millimoles of base. What's going to take place?
7.
Completely neutralized. Minus 10, plus 10. This becomes 0, this becomes 0, this becomes 10. Now, at this point, here's what you're tempted to go. pH is 7, it's neutralized. No, stop, no, pH is not 7. And here's the reason why. Because what's going to happen is that this part of the story is gone. Okay, that's gone, not part of the story. What is gonna happen is this, Mother Nature's sitting there and go, whoa, hello. It's the robbery situation. The anion is gonna go up to that water and go, it's just you and me now. Acid's gone, the hydroxide's gone. It's you and me, let's dance. So the anion comes up to the water and starts a secondary reaction.
Does that-
Okay? You want?
Does
What?
the secondary reaction only happen if there's no acid left?
Yes, and it only works if it's a weak acid, strong base.
What if there's base left?
Then we'll deal with that later,
Oh, okay.
okay? This only works when it is completely and exactly neutralized, okay? Now,
Can you have leftover base?
if you have leftover base, we'll deal with that later. Okay, do not complicate, do not muddy the waters right now, okay? Now, you have to start an entire new problem, okay? So what's gonna happen is the anion is gonna act as a base. It's gonna go up to the water, it's gonna go, yo, mind if I dance with your protons? Sure. Now, the anion is acting as a base, so what are you gonna have to use? Instead of the Ka value, you're gonna have to use the Kb value, okay? So there's a whole bunch of things that you need to do. You need to find the Kb value. That's one of the things. Now, here's the bigger truth. Here's a new rice chart. So what you have to have, listen to me, listen to me, listen to me. You have to have the actual concentrations of the anions. You cannot work in millimoles at this point. You have to go back to having the pure actual concentrations. So you've got to take those 10 millimoles and divide that by the total volume, which in this case is going to be 100 milliliters because I had 50 and 50. Okay? So if you do this math and you divide that out, this becomes 0.1 molar. Now, this becomes 0, this becomes 0. Now it becomes old school. Now you're back to old school. Now it's come full cycle. Minus x, plus x, plus x. 0.100 xx. Now, because the anion is acting as a base, you're going to go, I can play this game, Burkamp. So I'm going to have Kb equals x, which is my hydroxide, times my Ha, which is also x, divided by 0.100. Okay? Now, here's the kicker. How are you going to get that Ka value? You can take 1.0 times 10 to the negative 14th and divide that by your Ka value. So you have to get the Kb value by itself. That's going to equal x squared divided by 0.1. Now, here's the bigger kicker. When you get x, are you getting your hydronium ion concentration or your hydroxide ion concentration?
Hydroxide.
You're getting your hydroxide ion concentration. So, if you solve for x, trust me on this one, you get 4.0 times 10 to the negative 6th. If you take the negative log of that, you get a pOH of 5.4, which gets you a pH of 8.60. This is why when you neutralize a weak acid, the pH is not 7. The pH is above 7 because you start a secondary reaction that generates hydroxide ions, which you do not have to worry about if it's a strong acid. Evan,
And which Ka value would you use for that?
you'd use that Ka of acetic acid, or excuse me, of benzoic acid, of whatever that acid is that you start with.
Okay.
Now, if you have excess base, and this is going to be one of the problems on your assignment, if there's excess base, then take that excess base, however many millimoles that is, divided by the total volume, that is your hydroxide ion concentration. Because this is going to generate such a small amount relative to that excess base, it's not going to make any difference. Okay, so let me hand out yonder assignment.
Berg, why can the reaction only happen if there's no acid left?
What do you mean?
Why can the weak or the strong base only do its thing if there's no acid left?
Because, hold on. Let me get this done, then I'll explain that.
All right.
Take it.
There's some fundamental knowledge on WAC and FLM in town.
Do you have the assignment you're gonna be handing out tomorrow printed already?
Huh?
Do you have the assignment you're gonna be handing out tomorrow printed already?
I do.
Can I have it?
She's competing for a $64,000 scholarship.
I
can do that.
I'm so confused. Just like,
Okay, I still have the
okay, so let me get you started on these. So on this one, you have the first one. You have hydrochloric acid, sodium hydroxide, strong acid, strong base. Do not go, oh, what's the Ka value? There are no Ka values. Strong acid, strong base. Work in millimoles, moles. I care not. So all of those 1, 2, and 3. You're always strong acid, strong base. When you get to number 4, this is where you're going to have this benzoic acid problem, okay? You got 15 milliliters of 0.1 solution of hydroxide, okay? So this is the one where you're going to go through these stages. And what you're going to see is that as you go through these stages, you should see the pH go higher and higher and higher. And then you're going to draw a graph of volume of base versus pH on that. I'm done, you're on your own. I know you maybe Southies need to go.